Welcome everybody to problem set 10.1. All right, so here's our first question. Who should get welfare? A news article on a Gallup poll noted that 28% of the adults questioned felt those who were able to work should be taken off welfare. The article also said the margin of error for a sample size of 1548 is plus or minus 3 percentage points. Opinion polls usually announce margins of error for 95% confidence. Using this fact, explain to someone who knows no statistics what margin of error plus or minus 3 percentage points means. Okay. So there's a couple ways you could explain it. I'm going to say it like this. Margin of error of plus or minus 3% means if we conducted many samples of this size, the results would be within let's say 3 percentage points of the parameter. Um, 95% of the time. Okay, so that's what it means. You're going to do this over and over and over again, and if you did it an infinite number of times, 95% of your results would be within 3 percentage points of the parameter. Pretty simple. All right, next question. Hotel computer systems. How satisfied are hotel managers with the computer systems their hotels use? So they sent a survey to 560 hotel managers of this size hotel in Chicago and Detroit. They got 135 to return the survey. 2 questions concerned degree of satisfaction with their computer systems, blah, blah, blah. The managers responded on a 7-point scale, blah, 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 blah. All right, what do you think is the population for the study? Well, it appears to be hotel managers, right? Population is hotel managers. Okay. There are some major shortcomings in the data production. What are they? All right, well, the first thing you could see is they only asked hotel managers in Chicago and Detroit, which is not representative of the whole nation. So unless they're only interested in Chicago and Detroit, we have under coverage. Okay, so under coverage since they only looked at Chicago and Detroit. All right, next you'll see the survey was sent. Okay, so they sent this survey out and we only got 135 returned. Okay, so that's a bit of a problem. Okay. So non-response. 560. Okay. All right. These shortcomings reduce the value of the formal inference you are about to do. Correct. Okay, so this problem, again, is like the first homework problem. We're actually going to do some inference. So they're holding your hand and walking you through all the steps. So the steps are state your population, defend the validity of your data. So in this case, the data is not very good, and that's what we need to say. It reduces the value of our calculation. It makes our calculation in doubt. You still do it, but you just point out to whoever's reading your work that the calculation may not be accurate. All right, letter B. The measurements of satisfaction are certainly not normally distributed because they can only take whole number values from 1 to 7. Nonetheless, the use of confidence intervals based on the normal distribution is justified here. Okay, so again, they're holding your hand and they're telling you, hey, you're allowed to use a normal distribution here, but now they're saying, well, how come you're allowed to? Well, this was a big thing in chapter 9, right? The central limit theorem, yes. Assures approximate normality of the sampling distribution of X bar. Okay, we've said that many times and you will continue to say that over and over again. Okay, so even though only whole number values could be given, it will still look approximately normal as long as you have a large enough N. And we did have 135 surveys returned, so that's plenty large. Okay, letter C. All right, here's my mean. They want a 95% confidence interval. Assume the standard deviation is 1.75. Okay, so to get my 95% confidence interval, it's my mean plus or minus my critical value. In this case, we're saying it's a normal, it's a Z critical value from the central limit theorem. And that gets multiplied by the standard deviation of the statistic, also known as standard error. And of course, this whole piece of the puzzle is known as margin of error. So let's plug in our values. 5.3 plus or minus. Now we need our Z star for 95%. Again, we can find that from table A, we can find it from table C, or we can use our calculator to get it. So I'm just going to do a quick inverse normal. 95% means a tail of that to the left, right? It's 95, and then there's that 2.5 that we're missing. So there's my Z star, and if you looked it up on table A or C, you're going to get 1.96, and we use that over and over and over again, so you might end up committing it to memory, or not. You can always find it quickly. And that is 1.75, and our sample size was 135. And there you go. Okay, so there's your work. You can work it out by hand, or you can go into your test menu. These are some things we haven't really looked at much, but here it is, a Z interval. In this case, we have our stats. That was 1.75. Our mean was 5.396. Our N was 135, and we're doing a 95%. And there we go. Okay, but again, you do need to show this work right here. Whether or not you use that feature is up to you. So now, we would end by saying we are 95% confident. The true mean satisfaction is between 5.1 and 5.69. Okay. Okay, now one thing I do want to notice, I want you to notice, again, since this is the very first time you're doing this, it says use your inference toolbox. That's where students lose a ton of points. So I'm going to show you that real quick. It's back here in the book, which you should be reading. That page. Okay. And these are the steps to perform inference. Okay, step one, identify the population and the parameter. We identified our population. I guess we didn't identify the parameter. We should have said it's the satisfaction with the computer systems for hotel managers. Step two, choose the appropriate inference procedure and verify the conditions. Okay, that's what we were talking about when we're validating the data. Okay, and we said it wasn't all that great of data. We mentioned the normality, but we did not mention one important condition. So I'm going to go back right now, see if you can pick that out. All right. Okay, we did not mention if our standard deviation formula would be safe to use or not. Okay, that's, again, part of validating your calculation. So we hit on the normality. We hit on it's safe to use our standard deviation formula. And we did mention there's some problems with the data collection methods. Okay, then we do the correct inference procedure, which is what we did. And lastly, we interpret the results in context of the problem. And that's this bit right here. We're 95% confident that the true mean satisfaction is between this and this. I guess we should say for hotel managers. In Chicago and Detroit. And there you go. Okay. So anyway, most students love to just put the numbers in the calculator and spit out, here's the interval, and then move on with their lives. But if you do that, you will probably get an F, because that's only a small portion of all the work that you're supposed to do. So please follow that inference toolbox. All right, letter D. Different satisfaction. This one is with training instead of computers. There's the mean. Using the same standard deviation, let's do a 95% confidence interval. All right. So the population of interest, I should say, is hotel managers, and the parameter of interest is their satisfaction with training. Okay. Now, the other checks remain in place because the data is still 135 hotel managers, central limit theorem, so, and we still have the issue of the validity of this data due to our forms of bias. So I'll say C, part C for the other checks. Okay, now we're going to calculate. Again, it's X bar plus or minus my critical value multiplied by my standard deviation of whatever statistic I'm using. In this case, I'm using X bar. X bar was given to be 4.398. This time we're doing a 99%. How about instead of my calculator, this time I'll use the table just to mix it up. If I can find the table. There we go. So right there, my 99%, 2.576. And again, that's the number of standard deviations we need to go right and left to capture the center 99% of a normal distribution. And there you go, there's our work. Now you can use your calculator to get the actual interval. Okay, so we choose Z interval. Again, we're using statistics. We're changing to a different X bar. Same sample size, different confidence, 99% now. And there we go. So now we would say we are 99% confident the true satisfaction. Is that what we were talking about? Yeah, satisfaction. I misspelled it up there. Just like, what did I write? I was thinking stats up there. But anyway, satisfaction of hotel managers with their training is between 4.01 and 4.786 units of, I have no idea. Normally you're going to put some type of unit on that, but this is just like a scale, rating scale. All right, there we go. So there you go. That was our first look at formal inference. Hopefully that was exciting. All right, next problem. Healing of skin wounds. Blah, 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 blah. So we have 18 newts. There's the data. All right, question A, make a stem plot of the healing rates using split stems. So let's do that. Looks like we go from 11 all the way up to 40, it looks like. All right, so we've got an 11, we've got a 12, we've got a 14, we've got an 18. Again, this is a split stem, right? So I'm only going 0 to 4 on this row, and then this row would be 5 to 9s. Let's see, we've got a 22, a 22, a 23, a 23, 26, 27, 28, 29, 30, 33, 34, 35, 35, and 40. So there's our split stem. Looks all right to me. I don't see any major violations of normality there. But again, as they're saying, there's only 18 observations. So you're looking for major deviations. I don't see any. But here's the whole point of why we learned the normal probability plot way back when in first semester, because it's great to assess normality, and it's especially useful on smaller data sets when your other graphs don't really show it a lot. So put the data in there. Remember, it's the last choice right there. Okay. And there it is. And remember how to read that. Okay. You're putting it through an inverse normal transformation, so that should linearize it if it were normal. This looks fairly linear, so I conclude that the data set is approximately normal. Okay. This is the whole idea. We're saying with n of 18, we can't just say, oh, central limit theorem, right? We're kind of, again, working our way into that whole idea. So when we have a smaller data set, and if we have the data, we want to check for normality. Okay, so what do I find? I find it's approximately normal, right? The stem plot and normal probability plot show approximate normality. So again, they're kind of holding your hand here, walking you through steps. All right, part B. They usually assume that the animal subjects can be treated as an SRS, meaning good, valid, unbiased data. So treat these as an SRS. And let's give a 90% confidence interval for the mean healing rate of the species. All right, so B, the population of interest is newts, and the parameter of interest is the healing rate. Okay. All right. Now, there are certainly 180 newts, so we can use our standard deviation formula. Okay, and we discussed normality above, and they discussed the SRS for us. Right, so that's how we could validate our data. So let's do our calculation. So again, we're doing what are we doing? 90% confidence. Okay, so X bar plus or minus Z star. Okay, and our X bar, oh, we have to calculate X bar, but that's not a problem. We know how to do that. So there's our X bar, 25.6 repeating. And we're doing a 90%. I'll just use my table, it's handy. So there we are, 90%, 1.645. Standard deviations. And the standard deviation was 8, sample size was 18. There's my work. Okay. Now, to use my calculator, I would go again to test. I would again go to a Z interval, but now I can choose data instead of stats because I have the raw data. And that's going to be 8. The raw data is in list 1, and I want a 90% confidence this time. And there we go. Okay, again, you could work that out by hand if you want, but here it is nice and quick. So, state our conclusion in context. We are 90% confident. The average healing rate for newts between 22.565, what is this, microns per, oh, sorry, micrometers per hour. I'll say and 28.768 micrometers per hour. And there you go. Great fun. All right, letter C. A friend who knows almost no statistics follows the formula in a biology lab manual to get a 95% confidence interval for the mean. Is her interval wider or narrower than yours? Okay, so if you did a 90% interval, right? If you want to increase the confidence, well, that means you have got to get a wider interval, right? You need to capture more data in order to increase your confidence, right? So, pretty simple. Her interval must be wider to increase the confidence level. Right? And again, think, hey, if I want to be 100% confident, my interval becomes infinitely wide. Right? If I want to be 0% confident, I can say anything I want, really. Don't need any width. Okay. Right? And again, you can also think about it. The only thing that changes is this number right here. Higher confidence, you'll have more standard deviations here, right? Larger critical value. Larger critical value means wider interval. All right, next problem. More newts. How large a sample would enable you to estimate the mean healing rate of skin wounds in newts within a margin of error of 1 micrometer per hour with 90% confidence? Okay, so this one, we're not actually given the, we're not working with data, finding the interval. We're saying, hey, what sample size should I take, right? I'm interested in being this accurate. How large of a sample would I need? Okay, so remember, our formula for the margin of error is Z star multiplied by sigma over the square root of n, okay? And we need this to be within 1 micrometer, right? So it needs to be less than or equal to 1. All right. Now we have our Z star and we have our sigma, right? Z star is the 90% Z star, which is 1.645. And solve that, and we should get that n has to be greater than or equal to 173.19. And again, this is a sample size, so we cannot do 173.19. This is an inequality, greater than or equal to, so we must go up to 174. We would need a sample size of at least 174 to get a 1% margin of error at a 90% confidence level. There we go. All right, next, determining sample size. All right, so basically this is just like the last question, okay? So we've got, going for 95% confidence, we want a margin of error no greater than 3%, or sorry, 3 points. And then what they did is they started with a small pilot study to try to figure out what the standard deviation is, right? They found a sample standard deviation to be 12, so they're going to assume the population standard deviation is 12, right? This is kind of leading us into a future unit where we stop pretending to have that and we'll just go straight over here and there'll be one little tweak, but not a big deal. Okay, so the study budget will allow as many as 100 students. What would the margin of error for a 95% confidence interval be if we had a sample size of 100? Okay, again, margin of error, critical value multiplied by standard deviation over, in this case, square root of n. Okay, we're doing 95%, so 1.96 is our critical value. We're going to pretend sigma is 12. And n is 100. Okay, work that out. We should get 2.352. Okay, that's our margin of error. Okay, well, good news, that's less than 3 points. All right, letter B. There are many other demands on the research budget. If all these demands were met, there would be funds to measure only 10 children, not 100. What's the margin of error if we only had a sample size of 10? Okay, well, redo the calculation. And now all of a sudden, margin of error is unacceptably large. And this is what researchers often have to do. They have to juggle how much money they have and how they collect their data and how much data they're able to collect, etc. All right, and letter C, find the smallest value of n that would satisfy the goal of 95% confidence with margin of error 3 or less. Okay, that's what we just did in the previous problem. So 95%, 12 is a given, n is what we're gonna make our variable, and it needs to be less than or equal to 3. All right, so solving that, n has to be greater than or equal to 61.47, so that means, again, it has to be a whole number, so 62. The sample size to have a margin of error of 3 points at a 95% confidence level must be at least 62. There we go. All right, next question. New York Times included a box how the poll was conducted in one of its articles. Margin of error was plus or minus 3%, 95% confidence. There is our sample size. That's a good large sample. They did not include Alaska or Hawaii. Okay, in addition to sampling error, the practical difficulties of conducting any survey of public opinion may introduce other sources of error into the poll, right? That's why we spent a day talking about bias. Variations in question wording, okay, so there's one of the types of bias. Order of questions, for instance, can lead to somewhat different results, okay? So they're just kind of pointing out there can be bias whenever we deal with human populations. All right, letter A. This account mentions several sources of possible errors in the poll's results. List these sources. Okay, So they mentioned sampling error. Let's see, they mentioned question wording. They also mentioned ordering of questions. Okay, and of course, the way in which the questions are asked, if they're vocalized, matters too, right? And there's all kinds of other things, but that's what they mentioned in this particular write-up. All right, letter B. Which of the sources of error you listed in A are covered by the announced margin of error? Okay, so the margin of error covers only one error, okay? It covers random chance. In other words, sampling error, variability of samples. And that's important to understand. Statistics does not cover for bias. If there's bias present, you're out of luck, right? It's no good. Your results are bad. But sampling error is what is covered by your margin of error. Right? That's the whole point of it. We're saying if everything is good, the data collection is unbiased, good data, then random chance will put us here with whatever confidence we're stating. All right, last question. Use your calculator to find the confidence interval for the mean rate of healing for newts. I think we actually already did that. Okay, so do that again though, just to refresh your memory. So we go to stat, we go over to test, and we do our z interval, and we had our data, and we enter all of that. They want to say 90% still? Okay. And there you go. Okay, so that's how you use your calculator. Letter B, when you have the stats and not the raw data, that's when you choose stats, which I think we did that on this one as well. This was what, the hotel problem? What number was that? Page 5. Oh, this is a different one, page 549. Okay, so that's right here. So we're going to do a 99% confidence interval on this one. All right, so again, we go to stat, test, z interval. This time we have the stats instead of the data. And n is 114. What is, there's our x bar. Standard deviation is 3.4. Or sorry, 3.2. X bar is 11.78. N is 114. And we're doing a 99%. Okay, so that's how we use our calculator to do it. Do be careful. Yeah, they sent 160 questionnaires out. Only 114 were returned. So that's our size of our actual data. We don't have 160 responses, right? This has got non-response. There's always students on the test that put this number in for n, and that's not correct. That's how many pieces of data we actually have, 114. Okay, and there we go. That'd be our interval. So that's how we use our calculator. Again, you're going to use your calculator to save you time after you've shown the work, or you're going to use your calculator on a multiple choice question when you don't have to show work. But if that's all you write on a free response question, you will get 0 points. Okay, that's not just from me, that's from the AP exam. Free response requires you to show your work, and it also requires you, hey, look at the page I'm on, perfect, to follow these additional steps, identifying your population and parameter of interest, okay, verifying your conditions for the test you're performing. Right now our conditions are, of course, good unbiased data, normality, sample size large enough, population size large enough compared to the sample size to use our standard deviation formula. Okay, then state your, do your calculation and state your answer in context of the problem. For confidence intervals, that means state your confidence level and your result in context, okay? All right, that's a really important problem set, so make sure you know how to do it. And 10.2 will be an even more important problem set, so make sure you put in some quality time on these next couple of lessons. Thanks.